Hi there, it's repair time. I got two DATRON multimeters stacked here. A 1059 5.5 digit meter on top and a 1065A, a 6.5 digit meter below. Both, as often with these eBay finds, are very dead. I'm trying to fix the 1065A meter, and this is a log of what I was trying. A quick overview of what I was up against. The rear, which is on the right here, contains the power supply. This view is the underside of the 1065A with the IEEE 588 or GPIB bus interface below and the AC and ohms PCB above. On a 1061A, the empty spaces could hold other boards, like a current measuring or ratio measuring board, but the 1065A is the budget version of a 1061A and does not support any other boards. But at least those that it has are exactly the same as the 1061A. The front panel PCB, which actually has its own processor to drive the gorgeous Panaplex display. The top side of the meter contains the analog board on the top and the digital board on the bottom. So even on a budget 1065A, plenty of circuitry that could have failed. I said it was totally dead and there's no display or any other lights, but I can hear a relay clicking when power is applied. Standard practice says to check the voltage rails first, so I hooked the 5V rail. 0.96 volts. Clearly something is dragging this rail down, and most often the culprit is a shortened tantalum capacitor. By the way, the plus-minus 15V rails are fine, which accounts for the relay click. In hindsight, I should have noticed the significant AC part of the upper readout. 1.733 volts AC. That's unusual for a short somewhere on the logic PCBs, because that would not introduce so much AC. This points strongly to the power supply itself, but sadly I missed that clue and went on an extensive wild goose chase for a non-existing short somewhere in the crowded analog and digital meter PCBs. I followed the usual method by disconnecting PCBs and see if the fault disappears. That would indicate the short is on the removed board. Well, it's not the GPIB bus interface because the fault is still there. This was just the beginning of an exhausting search that I just want to summarize here. Here's a very simplified principle of how things are arranged in the 1065A. The rear PCB contains the power supply and wiring to the rear connectors. The display and keyboard PCB on the other side is self-explanatory. There are three PCBs that just contain traces and connectors, no components. One on the left side, one on the right side, and the center one. From the center PCB, multiple connections, I show here as yellow arrows, connect the analog PCB and the digital PCB. These in turn connect to the ohms and AC PCB on one side and a GPIB PCB on the other. I removed all boards except the display board, and the 5V supply would still be dragged down, pointing to a flaw in the display PCB, but all its transistors, diodes and caps tested okay. Removing the display processor, an 8279, from the socket restored the 5V. So, a bad processor? I actually had a spare one in my parts bin and replaced it, dragging the 5V down again. Two bad processors seemed unlikely, so is it the power supply itself? But how to disconnect the 5V rail completely from all the circuitry to check what the power supply does? This turned out to be very complicated because all connections to and from the gray PCB are soldered in. The whole 1065A is very maintenance unfriendly compared to the electrical identical but much better constructed 1061A that has connectors where the 1065A has soldered in wires to save a few pennies on connectors. It turns out there's one point at the top end of the center PCB where there's a small wire loop soldered in that runs most of the 5V. So the first action was to cut this loop. That helped, but there was an additional wire that ran 5V. In fact, there were two, but it turned out that the second 5V are different and belong to the high voltage supply of the Panaplex display. Just to be on the safe side, I desoldered both of the 5V wires. With that done and the 5V supply now completely disconnected, I hooked the multimeter to the 5V rail at the power supply side, and after powering on, I now got almost 5.3 volts. So it's not the power supply after all? But after having gone through all the trouble of isolating it, I decided I'd better give it a good load test before declaring it working and searching elsewhere. That test was in form of a 50 ohm load resistor outside of the frame, which at 5 volts draws a moderate 100 milliamps. And whoops, the nice voltage collapses to just 2.1 volts and we have almost 2.5 volts AC again. So this power supply is definitely broken. But before trying a repair, I decided to feed 5 volts from an external supply. That way I know if there are any other flaws in this meter, for example one that might quickly kill a newly repaired power supply. So for this I temporarily reconnected the blue wire because the Panaplex 5 volts was fine, and connected external 5 volts to the red wire and the part of the cut loop that is away from the internal power supply. The moment of truth. Applying power to the 1065A first for the other voltages, and now my external 5V power. And to my great relief, the meter seemed to work. And it responded to key presses. The 5V power draw was about 600 milliamps. Please ignore that resistor I had left connected from some previous use. A quick look at a part of the power supply schematics of the meter. As I mentioned before, the plus-minus 15 volts rails are fine and not on this view. The failed part is the regulator labeled MC7805 here. Above it is the part that powers the Panaplex display. It has its own plus 5 volts on top, which is the blue wire I showed earlier, and a feed from the plus 5 volts from the failed MC7805, which was the red wire. Identifying the regulator on the tightly packed area next to the mains transformer revealed a surprise. This does not look like the TO220 package of an MC7805. It's something in a big TO3 package instead. Using a boroscope camera, I managed to get a view of the label. It's an LM309, which is a 5V regulator in a TO3 housing, good for up to 1.5 amps current. Fixing the defect regulator would normally be a straightforward exercise, but not on the 1065A. For that, you have to remove the PCB, and that's next to impossible. There are many tens of wires that are soldered directly into the board, again to save pennies. Some are not even color-coded, so you have to attach your own labels to not mix them up. And replacing the regulator without taking everything apart is impossible too, because of the tight spacing between the plate that mounts the LM309 and another small transistor, and the thinner metal sheet immediately to the left, which is the heatsink for another power transistor from the Panaplex power supply. In the end, I decided to just leave the LM309 in place, but disconnect it so it can't cause any further harm, and simply construct a new 5V regulator board that connects after the rectifier and smoothing caps of the old one. I managed to desolder the white wire to the input pin of the LM309 from the PCB and the black wire directly from the LM309 output pin. I insulated those two wires with blue heat shrink tubing, and now, with those two wires removed, it's possible to see a bit more. I noticed that especially around the input pin there's some sort of white residue, almost as if a cap had leaked, but there is no cap anywhere close that could have done that. Maybe it came out of the LM309 itself as it failed. Who knows? In any case, I'm glad it's disconnected. For my new 5V regulator, I decided to mount it in the gap between the rear panel and the rear PCB. To avoid drilling new mounting holes, I decided to use the ones for the Made in England label after drilling out the rivets. This is the frame of the new regulator that will be mounted there. Two arms of clear perspex plastic provide insulation of the heatsink that holds it. This time it's a real 7805 regulator. Adding the necessary decoupling capacitors and an additional smoothing cap similar to the one that was in the original power supply. The new regulator installed and wired up. I was curious how hot my new regulator would get, so I added two thermocouples, one on the heatsink directly and one close to the large capacitor which is part of the plus minus 15 volts rail. During that test, the lid was closed, of course. After about 2 hours, the heatsink was stable at about 75 degrees Celsius or 167 degrees Fahrenheit. The worrying part was the temperature at the capacitor, which, while also stable, had reached 50 degrees Celsius or 122 degrees Fahrenheit. That was a little hot, and I decided to move the regulator away from that location. I found 2 unused screw holes in another part of the rear area where not much is located. To be able to reuse my regulator, I fabricated a bracket to match the previous screw holes to the newer, wider pitch. That's how the new regulator looks, with a bracket attached temporarily. And that is how it looks mounted in place. The screws all have to be countersunk to make this work. Nothing can be protruding, or the bottom panel of the meter won't fit anymore. When the meter is running, the DC input voltage to the regulator is just over 10 volts. So 5 volt excess voltage have to be converted to heat. At a power draw of between 0.5 and 0.6 amps, that means between 2.5 and 3 watts. While 75 degree heatsink temperature is not excessive, I would like to run the regulator a little cooler. Given that the meter is what it is, the only way to do that is to reduce the input voltage. One way of reducing the input voltage is to use a resistor to drop a bit of the excess voltage. Since that drop is current dependent, more current, more drop, one needs to be a bit careful not to cause too much drop right when the regulator needs its input most. In the end, I decided to use 2 1 ohm 5 watt resistors in series, mounted a little haphazardly next to the regulator, so they could be easily changed if needed. The 2 ohms dropped the regulator input by about 1 volt to 9 volt. Of course, the overall excess heat has not changed at all. What I did is move some of the heat produced from the regulator to the resistors, but they can handle that easily and the regulator can now run a little cooler. But that's the theory. To find out if that worked, I repeated the test with the thermocouples, one in the heatsink and the other back in the area where the big capacitors are. This graph shows it worked at least a little. The temperatures for the old location is shown in red and the new location in blue. The solid lines are the heatsink temperatures and the dashed ones the temperatures at the capacitor. At the new location, both heatsink and capacitor temperature have dropped by about 5 degrees Celsius or 9 degrees Fahrenheit. Not much, but hey, every little thing helps. Before closing my repaired 1065A, I thought it might be a good idea to replace the battery. The meter keeps its calibration data in RAM and the battery keeps that alive while the unit is powered off. This unit might have been sitting switched off for a very long time. The battery is soldered in. Normally you should never solder something while the power is on, but there is not much choice here. The 1065A has to stay powered on to allow me to remove the battery, or I lose the calibration data. Using a normal mains-powered soldering iron is a problem here. The tip of a mains-powered soldering iron is connected to ground for safety. That means if the negative pole of the battery is also connected to ground, which is likely, touching the positive pole with a soldering iron while the unit is on is going to short circuit the battery and the RAM supply pins, which means at the very least goodbye to the calibration data or worse, damage. The option is to run either the meter or the soldering iron through an isolation transformer or get a USB powered soldering iron. I would need such a soldering iron so rarely that I can't justify buying one of these fancy USB irons, but this one does the job even though it's only 8 watts and I paid even less when I bought it. Of course, for this job one must not plug it into a mains powered USB power supply, but instead power it from a power bank to remain isolated. The wire is tightly wrapped around and due to the low heat capacity the small soldering iron struggles a bit, but in the end I succeeded. The new battery has more of a flat ribbon kind of connection, which makes soldering in even more challenging. But the tiny iron worked well enough, and I'm glad that after the second connection is made, the precious calibration data is now safe again from power fails. Amazingly, this 3.7 volt battery still holds nearly 3.7 volts, even though the date code of 082 seems to indicate it was made or expired in April 1982, 42 years ago. A bit unlikely. I rather think this code may mean 82nd day of 2004 or something like that, which is only 20 years ago. The manual states one should indicate the date of the next battery replacement on the rear panel. That date is 5 years after the date of installing the new battery. So this label indicates that the battery was last replaced in 2003. If that is true, that battery is 20 years old and should have been replaced 15 years ago. A 2003 installation date would also mean that the 04 code on the battery is probably the expiration date. I peeled the label off and this uncovered the original renewal date from the factory. That 1991 date indicates my meter was made 5 years earlier in July 1986. The meter works now and I'm quite happy with it. I have run it for hours and the new power supply seems to be holding up. I just love the Panaplex display, which is clear and very easy to read, even from a distance. As you can see, the unit passes its self-test. The 1065A is quite easy to use, in part of course because all the more advanced functions of the 1061A have been removed. It does just DC and AC volts and ohms. Here I am measuring DC volts. Switching between auto and manual ranges is pretty self-explanatory. Since this is an A model, pressing the filter button makes it a 6.5-digit multimeter. The spec function computes the uncertainty of the measurement. Basically, the meter has internally a table of its spec and uses that and the time since the last calibration to do that. The time, incidentally, has to be set by a switch on the rear panel between 24 hours, 90 days and 1 year. I set it to 1 year. That ugly thing above is the key switch to turn the meter into calibration mode. It was plastered full with cal stickers and I have not found the time to clean it properly. Also, since I relocated my regulator, I reinstalled the previously removed Made in England label. Using AC is just as easy, and to get AC plus DC, both buttons have to be pushed in at the same time. The 1065A can do 4-wire measurements. These I plus and I minus terminals are only for 4-wire ohms, not for current measurements, as the 1065A cannot measure currents. Here I am using 2-wire ohms. And this is a 0.5 ohm resistor using 4-wire mode. The min and max button do the usual thing, but the 1065A has an interesting mode when both are put on simultaneously. In this case, it shows the difference between max and min, a kind of peak to peak, since the last reset. What it shows here is the drift, not the absolute value of a resistor in 100 microohms. And that's it for this repair. If you like my videos, don't forget to subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided becoming a Patreon. That would really help this channel. Thanks for watching.